Hello, you're listening to the Science of Everything podcast, episode 124, Volcanoes. I'm your host, James Fodor. Now, in this episode, we are, as the name indicates, going to talk about volcanoes. In particular, I'm going to talk about the nature and causes of volcanoes, the different types of volcanic eruptions, and the related different types of volcanoes that are formed by different types of eruptions. Then we'll discuss a little bit about some of the different volcanic landforms that can be formed as a result of volcanic activity, and conclude by talking about a few case studies of particularly important or well-known volcanic eruptions. The recommended pre-listening for this episode is episode 111 on plate tectonics, which will give a bit of a background about some of the underlying mechanisms that power volcanoes ultimately. So I'm not really going to be talking about the plate tectonic side of it too much. I'll just make a few references here and there to, diverging and converging plate boundaries and such. But in this episode, what we're really going to focus on are volcanoes as such and that specific phenomenon. All right, so that being said, let's make a start and talk about sort of what is a volcano and what causes volcanic eruptions. Many people are familiar with volcanoes, but perhaps haven't thought about exactly how to define one. A volcano is defined as a rupture in the crust of Earth or another planetary object, but here we're just going to be focusing on Earth. And this rupture allows hot lava, ash, and gases to escape from a chamber below the surface. So this notion of a magma chamber is very important for a volcano. If there's no magma chamber, you can't have a volcano. Magma, you may recall, is just essentially molten rock, and molten rock is what is under most of really all of the surface of the Earth, depending on how far you go down below the crust. Again, you can see the episodes on plate tectonics where I talk more about that. But the basic idea is that the Earth's inner layers, which consist of magma, are surrounded by the outer layers of crust, which is various types of rock and silicates and so forth. In certain locations, for various reasons, gaps form in this outer crust, allowing magma to come to the surface or near the surface, forming a magma chamber. And under certain conditions, which we'll talk about in a moment, the magma, as well as hot ash and gases and other things, escape from these magma chambers, erupting to the surface or sometimes underwater, forming a volcano. Often we think of a volcano as the mountain or hill or other visible external structure that's formed as a result of a volcanic eruption, but that is not actually the volcano. That's typically the sort of remnants of previous eruptions, which is part of the volcano, but the volcano itself is really the rupture and the magma chamber below, as well as sort of whatever's has been piled on top of that. So just bear that in mind, and we'll sort of illustrate that distinction a little bit more as we go through the episode, particularly talking about the different types of volcanoes. Now, volcanoes can form as a result of a variety of different mechanisms, depending on essentially how the rupture is formed that allows the magma to rise up through and penetrate to the Earth's surface. Typically, volcanoes form at the boundaries between tectonic plates, either when they're diverging or when they're converging. Divergent plate boundaries are typical at the mid-oceanic ridges, as again, see the previous episode on plate tectonics, where the plates are moving apart from each other. So that's a in fact, most of the Earth's volcanoes are under the ocean at the mid-ocean ridges. But you can also find many volcanoes at converging plate boundaries, especially if you have converging oceanic continental boundary activity, as is found around much of the Pacific, resulting in what's often called the Pacific Ring of Fire, where many volcanoes are found. So this encompasses a wide range of areas, including Japan, the Philippines, parts of Indonesia, the eastern United States, and parts of Peru and down the Andes. So in these locations, basically what happens is that you have, in the case of a convergent plate boundary, one plate is subducting under the other. Often the oceanic plate will be subducting under the continental plate because the oceanic plate is thinner and denser, so it's lower down on the mantle. And as that happens, water is dragged down by the subducting plate, and that water is thought to lower the melting temperature of the mantle that is above it, because it's being subducted down, thus turning it from a solid into a liquid, and thus creating magma. And that magma then, because it's less dense than solid, sort of rises up and eventually, or sometimes at least, it can reach the surface of the Earth. Sometimes it solidifies again at depth, forming igneous rock or igneous intrusions. But when it reaches the surface of the Earth, it can form a volcano. So basically, the long and the short of it there is that at convergent plate boundaries, so like Pacific Ring of Fire and many of the many land-based volcanoes, you've got one plate subducting onto another, pulling down moisture, pulling down water with it. That water, as it's released and spreads around, alters the melting temperature of the mantle surrounding it. This leads to the mantle turning into liquid, so forming a magma, which then, because it expands, rises up and sometimes reaches the surface. So that's the cause of many of these sorts of volcanoes. With the divergent plate boundaries, typically along the mid-oceanic ridges, but they occur some places on the Earth's surface as well, it's more a situation of convection currents which are causing the plates to move apart in the first place, upwelling or leading to the rising up of magma, which at the thin regions of crust just between the boundaries can reach the surface of the Earth, or at least reach the bottom of the ocean, and some of that magma comes up. Now, there's a third kind of major type of volcano, or at least in terms of the mechanisms of why the volcanoes occur, and these are called hotspots. So these are sort of the least well understood types of volcanoes because they don't occur at plate boundaries. Hotspots occur in the middle of a plate, and so it's sort of a bit of a question, well, why is the magma rising up there when there's no gap between the plates? But it's thought that these are caused by mantle plumes, which are columns of hot material that are rising up because of convection currents in the Earth's mantle. And just because of sort of happenstance of where these are located, there can be places where these upwellings of hot material occur just, in the middle of a plate. And when there's sufficient pressure and when there's enough of that material coming up, it can essentially burst through and form a volcano. And so this is thought to be the origin of the Hawaiian Islands, which occur in the middle of a plate, or middle of an oceanic plate in that case. But this can occur over land as well. And so because the overlying plate is moving relative to these mantle plumes, what you get is that the volcano on the surface of the Earth or on the ocean appears to sort of move over time. And that's just because of continental drift. So this is why you get these volcanic chains of islands, such as the Hawaiian Islands, where the volcanic activity sort of moves over geological time as the oceanic plates gradually move across the underlying mantle plume. So those are some of the main causes or underlying causes of volcanoes, basically convergent, divergent plate boundaries, and hotspots. Now, these can give rise to different types of eruptions. And in fact, that there is quite a sophisticated classification of different types of eruptions, which I'm not going to go through in full detail. I'm just going to mention some of the main types. And the single most important distinction to be made in terms of types of volcanic eruptions are explosive eruptions and effusive eruptions. Explosive eruptions are probably the most well known, at least in most of the world. And these are the ones where you have a big boom, basically, an explosion, and you have lots of smoke and ash and everything going all over the place. So sort of your stereotypical volcanic eruption. These are characterized by explosions caused by the expansion of gases that are coming out of the magma, which then propel the magma and other material, across a wide area. Effusive eruptions don't have the same gas-driven explosions or big clouds of ash and things like that. Effusive eruptions are much slower and less violent, and basically they are characterized by the gradual release of lava without much in the way of explosion or creation of gases and hot ashes and so forth. And these are the type of eruptions, these effusive eruptions are more characteristic of Hawaiian volcanoes, for example. So they're sort of slower, less violent, and typically occur over a prolonged period of time. They produce a lot of lava, but not much in the way of explosions and gases and ash and so forth. Now, we've talked about the fact that volcanoes are ultimately caused by movement of magma at locations where the magma can ultimately rise to the Earth's surface. So typically that's at plate boundaries, but sometimes it can occur in the middle of a plate when you have those mantle plumes. But there are more specific mechanisms that actually give rise to the eruption per se, because having magma come near to the surface of the Earth or pool up in a underlying magma chamber, that by itself doesn't lead to a volcanic eruption. That's sort of necessary for a volcanic eruption, but it's not sufficient, right? So when we talk about the particular mechanisms by which eruptions occur, there are sort of three main ones that have been studied. The first is a magmatic eruption. And this is sort of the most common, or at least the most well-known type. And this occurs due to decompression of gas within the magma that propels it forward. So basically, when the magma reaches a certain temperature or pressure or composition, it obviously depends on a lot of factors there, the gases that are dissolved within the magma decompress and then rise up to the surface. And that sort of brings the magma with it or propels it forward, leading to an explosive eruption. So that's ultimately driven by decompression of gas. Now, there's another mechanism, which is kind of the opposite of this. This occurs as a result of the interaction between water and magma. So when water comes into contact with magma, that leads to a thermal contraction of the magma because it's cooled down by the water. This interaction between the water and the magma then can become quite violent, leading to an eruption. The exact mechanisms of that, as far as I understand, are not properly understood. But the key distinction between the two is that the first type of magmatic eruption involves decompression of gas within the magma, which then sort of forces it all upwards or forwards. Whereas in the second case, you have an interaction between water and magma, which actually causes contraction of the magma, which can nevertheless lead to then the violent eruption. Now, the third type, the names are a bit weird, so I won't give all of the names, but the third type is caused by superheating of steam when it comes into contact with magma. And this is distinct because this doesn't typically lead to the release of any new magma. It more causes an explosion which blows apart existing rock in the volcanic conduit or in the form of magma chamber or wherever. That's a bit of a different mechanism. So if you want to think about it, that there's sort of the decompression of gas or interaction with water or superheating of steam. So the sort of three main mechanisms that lead to the actual eruption itself. In all of the cases, in order to have an explosion, you need expansion of what typically gases. And so it's more about the mechanism of how that occurs, where it's the decompression of gas directly or interaction of the magma with the water or superheating of steam. In all of those cases, you can get explosions. Exact nature of those will differ depending on the specific case. Now, once you have a volcanic eruption, there's sort of three main classes of material that are expelled. The sort of most obvious one is lava, which is magma that's on the Earth's surface and then flows over the sides of the volcano or can be propelled some distance away. Volcanic gases, which is a mixture typically of steam, carbon dioxide, and various sulfur compounds, are also very important constituent of the volcanic material and are often much more dangerous than the lava, as we'll talk about a little bit later. The final component is tephra, and this is particles of solid material of different shapes and sizes which are ejected and thrown through the air. So this is essentially looks like smoke particles or bits of rock that are thrown. There's different names of tephra depending on the particle size. So very small particles are described as ash because they're basically like ash. Although in this case, it's not typical ash that we think about as produced by a fire, which is mostly carbon. Volcanic ash, on the other hand, is basically tiny pieces of rock, so it's much heavier and denser, which is why it's dangerous to have volcanic ash collecting on the roof of a building because it's extremely heavy and can easily lead to it to collapse, as distinct from ash from a fire, which is not particularly heavy. Intermediate particle sizes are called lapilli and have a size between a few millimeters up to about 6 centimeters or so. The largest size, which are larger than around 6 centimeters, are called bombs. And these are basically large pieces of hot rock, which can be thrown out by a volcano and can be, well, as dangerous as a bomb, really, which I think is an indication that you best avoid them. So to recap, we've got the volcanic gases, which is steam, carbon dioxide, and sulfurs. You've got your lava, which is liquid magma, and then you've got tephra, which are basically solid pieces of rock of varying sizes from ash up to full-on bombs, which are thrown all over the place. Now, one of the most dangerous aspects of a volcano are what are called pyroclastic flows. So pyroclastic flow is basically a very rapidly moving current of hot gas combined with tephra. So the tephra can be different sizes, from the small ash particles to the big bombs and kind of everywhere in between. And what typically happens is that these are released by a volcano, and then they, either from falling down the side or being ejected sort of sideways, move down a hill at very rapid speeds, at typically about 100 kilometers an hour, but they can be up to 700 or 800 kilometers an hour, and at temperatures of around 1,000 degrees. So that if you sort of see them from a distance, it looks like it's just sort of smoke, but it really isn't. It's very rapidly moving, very hot pieces of rock. So it's much heavier than smoke, it's much hotter than smoke, and much faster moving as well. And as I said, they're the most deadly of all of the volcanic hazards because they easily suffocate or just crush people, burn them alive if you get caught up in them when they're still very hot. And it's pretty much impossible to escape them because of how fast they move. So these are typically what causes the majority of deaths in the most dangerous volcanoes, such as Mount Vesuvius being a classic example of this, when you had all of those people buried under tons of this of the pyroclastic flows, which then solidify. So that is the first sort of category of materials that are ejected by volcanoes, the tephra. Now let's talk a bit more about lava, which is molten magma which has reached the Earth's surface. So lavas range in temperature from about 800 to 1200 degrees Celsius, so about 1000 degrees, similar in temperature to the pyroclastic flows. And they are, by definition, fluid when they first erupt onto the surface. Eventually they will cool down and become more viscous and then solidify. When you see lava, it typically doesn't look like the way lava is often portrayed in movies. In fact, the way you often see lava portrayed in movies, and I've even seen this in other contexts as well, where people talk about lava, it is more like what molten metal looks like. You know, the sort of yellow, orangey, very fluid substance that looks very hot. But lava is not molten metal. Lava is molten rock. It's not as hot as molten metal, but it's a lot hotter than, your typical oven or other sort of organic fires. And so what actual lava tends to look like is when it's fresh or just erupted, it will look sort of yellowy red. But very quickly, it develops an insulating crust of solid rock that's on the top of it. As a result of radiative loss of heat, as the very outer layer sort of solidifies. But under that, it's still liquid, and so it's still flowing. And so you will see it move. It kind of looks like the Earth has turned to liquid and the ground is just sort of moving. Because it looks, the outer crust layer looks fairly dull and sort of crumbly. Although obviously it differs between different types of lava that I'll talk about in a moment. Only when you have very rapidly moving lava, or when it's just freshly produced, or if it's been disrupted in some way, like you throw something into it, will you actually see what underlying fluid looks like as distinct from the sort of crust that forms on the surface of it. So 3 main types of lava, which differ according to their composition. Two of them are named after Hawaiian terms that were historically used and have become technical terms in literature. So there's Pahoehoe and A'a. I think that's how it's pronounced. The second is spelled with 2 A's. There's some diacritics as well. It's basically 2 A's if you want to look that up. And then there's a third type called block lava. So Pahoehoe is smooth and ropey looking, and it moves the most rapidly. It's the least viscous. A'a is sharper and blockier. It moves more slowly because it's more viscous. And then the block lava is the most viscous of all. It's kind of similar to A'a, but it is even more viscous, and the pieces are kind of more angular and a bit smoother sided. So it sort of looks the least like lava. It kind of looks like a whole bunch of stones just sort of moving down the slope. But again, that's because that's on the surface. Underneath it, there's your liquid lava. But they move at different speeds because of the different viscosity. And as we'll get to in a moment, that's ultimately dependent on the chemical composition of the magma, and particularly the silica content. Essentially, the higher the silica content, silica being silicon dioxide, SiO2, which we've talked about in previous episodes as being extremely important in determining the properties of different minerals and rocks. But the silica content of magma and lava is primarily what determines both its temperature and also its viscosity. So the higher the silica content, the cooler it will be, but also the more viscous. Pahoehoe being the least viscous, or the runniest, if you like, tends to have the lowest silica content, whereas the A'a has high silica content, and block lava the highest of all. There's another type of lava, I don't know whether it's really defined by composition, but more so just where it's found, and this is called pillow lava, which is found in lava flows underwater. The interaction of the magma with the water forms these sort of big pillow structures, which look pretty funny. Now, lava flows are dangerous because of mainly how hot they are, and also, again, it's rock, so it's very heavy, and very hard to divert lava flows of any size because of that. However, typically they are not as dangerous as, particularly as pyroclastic flows, because they're quite slow moving. Even the runnier pohoi types of lava still move this ones still move relatively slowly, which gives people time to respond and get out of the way. So typically they may, if there's an eruption in an unexpected location, you may have loss of property, but typically much lower loss of life. It's the big explosive eruptions with the big pyroclastic flows and the volcanic bombs falling everywhere. Those are the really dangerous ones. I've now talked about some of the different aspects of volcanic eruptions, including the different types of the eruptions and the various materials that are ejected, including gases, lava, and the tephra. Now I want to talk a little bit about volcanic activity before moving on to the types of volcanoes. So you've probably heard about the distinction between active volcanoes, extinct volcanoes, and dormant volcanoes. So active volcanoes are those that are essentially currently erupting. Now the problem with that is that there's no real consensus on what counts as currently. It certainly doesn't mean that it's erupting like literally this minute. It doesn't even mean that it's erupting this year or even this century, because basically volcanoes, depending on their size, can erupt and then go millions of years between another eruption. So it's sort of unclear how to exactly determine whether a volcano is currently active or not. Typically, the phrase will be used to refer to one that we kind of know has erupted recently and expect to erupt again in the not too distant future. But the term is pretty loose, and it's very hard to distinguish between an active volcano and one that's dormant and one that's extinct. Usually the phrase extinct volcano will refer to one that we think is very unlikely to erupt again, particularly if we know that it no longer has a magma supply. So remember I talked before about the fact that in order to erupt, a volcano has to have a supply of magma being replenished from the Earth's mantle. Without that, the volcano cannot erupt. And so typically, if that was known, then we'd describe that as an extinct volcano. However, the mere presence of magma or ability of magma supply doesn't entail that the volcano is going to erupt. It's necessary, but not sufficient. You also need the right conditions. And it can be very hard to determine whether those conditions are going to facilitate an eruption or not. So dormant volcanoes are typically those that have not erupted for quite some time, often thousands of years, but are thought to be likely to erupt again. So Yellowstone would be a good example of this. So again, you've got active volcanoes, dormant volcanoes, and extinct volcanoes. And the boundaries between those are quite difficult to establish. But you can think of an active volcano as one that has erupted recently and we expect to erupt again. Dormant, it hasn't erupted recently, but will erupt, or we think will erupt again sometime, quote unquote, soon. And extinct volcano, we don't expect to erupt again. But there have been quite a few times when volcanoes that were thought to be extinct then erupted anyway. So it's quite difficult to know. All right, now let's talk about some of the different types of volcanoes, having talked for a while about eruptions. I've already mentioned the fact that there are different types of lava depending on the chemical composition of the magma, and particularly its silica content. The chemical composition of magma tends to change over time as a result of it moving around and interacting with other materials. It also depends on the source of the magma, for example, whether we're looking at a convergent plate boundary or a divergent plate boundary, such as the mid-oceanic ridges, or whether we're looking at a mantle plume coming up like the Hawaiian Islands, in the middle of a tectonic plate. All of that's going to affect the chemical composition. But the very basic idea of the different types of volcanoes and the connection with the chemical composition of the lava is that the more viscous the lava is, and therefore the higher the silica content it has, the longer the pressure will build up before it's able to be released. And as a result, you will get explosive eruptions. Remember I talked before about the difference between explosive and effusive eruptions? Well, explosive eruptions tend to occur when you have silica-rich, viscous lava, which builds up in the magma chamber, or just above, over time, and then reaches a critical point where the pressure is released and it explodes. Effusive eruptions tend to occur when you have low silica content, non-viscous, that is runny, lava, which doesn't build up over time or only to a small extent, and therefore is able to regularly release the pressure, so you don't have an explosive reaction. So it's kind of intuitive there, right? If you can release the pressure off slowly over time, you don't get those explosive eruptions. Instead, you get the effusive, longer drawn out, lower intensity eruptions. So that's the connection between the type of eruption, the composition of the magma, and also the type of volcano that is formed. So let's now talk a little bit about that. There are sort of four main types of volcanoes that I'm going to talk about here. So there are shield volcanoes, cinder cones, composite volcanoes, which are also called stratovolcanoes, and lava domes. So let's start by talking about shield volcanoes. Shield volcanoes are so named because they are wide and flat like a shield. Not totally flat, but only slightly rounded. Imagine laying a shield out, on its back and spreading it out over your table. You've got a modest curve across the table, but over a wide area. That's your shield volcano. Shield volcanoes typically are formed when you have low silica content, runny lava, which do not explode catastrophically. So therefore, we're talking about effusive eruptions, relatively gentle eruptions. And because the lava is not very viscous, it flows very readily and so doesn't build up very much. It flows over a wide area, which is why you have that sort of flat shield shape. And shield volcanoes are more common in oceanic crust because oceanic crust typically has a lower silica content. So this is a bit more characteristic of your divergent plate boundary mid-oceanic ridges volcanoes, although you won't often see those resulting volcanoes because they're under the ocean. The Hawaiian Island volcanoes are also typically shield volcanoes, again, because in those cases, you have relatively low silica content. So as you kind of move upwards relative to the mantle, you typically, obviously this is just a generalization and there are exceptions depending on the specifics, but you typically get less mafic, that is less silica deprived rock and more silica enriched rock as you go from the mantle up through, say, oceanic crust up to your continental crust. So when you're talking about a mantle plume, such as occurs in the Hawaiian Islands, which is the cause of the volcanoes there, you're more likely to get these shield volcanoes because of the relatively silica impoverished material that's erupting there. Whereas when you have convergent plate boundaries between, say, oceanic and continental crust, when you have the continental crust material that's interacting with the water that's coming up from as a result of the subducting oceanic plate, that's when you're most likely to get these highly silica enriched, highly viscous magma and then lava coming up to the Earth's surface. Anyway, so that's the shield volcanoes. The kind of next level up in terms of silica content are your cinder cones. Now cinder cones are often not sort of found by themselves. Often they're found as sort of like mini volcanoes surrounding larger ones. Most cinder cones only erupt once, which is kind of why they're smaller, only 30 to 300 meters high or so quite small compared to many of the other types of volcanoes, which can form huge mountains or sort of very large regions like the shield volcanoes. But these cinder cones form as a result of fairly mafic to somewhat intermediate, so like middling range in terms of silica content. And sometimes they form, as I said, on the slopes of big shield volcanoes. Next level up then are your composite volcanoes, or as I said, stratovolcanoes. Now these are tall conical mountains, more like what you typically think about as the stereotypical volcano, or at least a lot of people, I think of that as the stereotypical volcano. These volcanoes are comprised of alternate layers of lava flows and tephra in alternating layers, which is why it's called a stratovolcano. It has multiple strata or layers. And they have quite steeper slopes. Typically, they are formed from intermediate magma, so middling amount of silica content that allows the lava to be more viscous and so allows it to have a steeper slope because, again, the runnier it spreads out more. There is a combination of lava ejection as well as explosive ejection of pyroclastic flows and other tephra, which is what gives its stratification, its series of layers. So you don't get all of one or all of the other. Shield volcanoes is pretty much all lava, but in composite volcanoes or stratovolcanoes, you get a mix of lava and then tephra, which then builds up this big sort of conical mountain shape. And this could be very large. Then at the furthest end, so the most silica-enriched type of volcanoes, typically in terms of the material that produces them, are called lava domes. And these are typically circular mounds which form as a result of slow extrusion of very viscous lava. And as I said, one way that they can form is by high levels of silica in the magma, but that's not the only way. They can also form by degassing of fluid magma, which we won't talk too much about, but that's the gas coming out of the fluid magma, which can lead to this structure as well. So they're not exclusively formed by high silica lava, but that is one way that they can be formed. And so these are quite common, especially at convergent plate boundary settings. Remember I said that when you have the convergent plate boundary, you've got more, typically because of the continental crust, you've got more silica-enriched material, so you typically have the viscous lava, and so more likely to form these lava domes. So to summarize there, you've got your shield volcanoes, which are formed by lots of runny lava and they're sort of fairly flat. Then you've got your lava domes, which are formed by lots of viscous lava, which are therefore steeper and kind of have a big crater at the center where the lava's come out. And then you've got your composite volcanoes, which are formed by a combination of lava flows and pyroclastic flows and ejection of other tephra. And then the fourth type were the cinder cone volcanoes, which are typically a lot smaller and only erupt once and can be found often, although not always, surrounding other volcanoes, like shield volcanoes in particular. Now, there is kind of another type of volcano, though it's not exactly a volcano per se. It's called a volcanic fissure or a fissure vent. And often this is basically just like a hole where the magma comes through. Often they can be extremely long, so a few meters wide, but many kilometers long. And they can cause very large flood basalts, which are very large regions of basalt coming up and then solidifying on the surface. So I don't know whether those count as volcanoes per se, but I thought I'd mention them as well. But the four main types, as we talked about, are the shield, composite lava, and the cinder cones. There are also other landforms that can be caused by or the products of volcanic activity, in addition to the volcanoes themselves. And so now we'll turn to talking about some of these. The first is the caldera. Now, a caldera is a large hollow structure which forms as a result of the emptying of a magma chamber following a large volcanic eruption. Remember, the magma chamber is just basically a region like a hole in the ground where the magma pulls up, and eventually, when the pressures becomes extreme enough, explodes and you get a big eruption. If the magma is viscous enough and other factors, right? But the point is, once that eruption has occurred, that material is no longer underground. It's been extruded, right? It's sent up above the surface. And so when that happens to a significant enough extent, basically there's just now a hole in the ground, and the magma chamber then collapses, and the material on top of it falls down into the partially emptied or completely emptied magma chamber, leaving a big depression at the surface of the Earth. So a caldera can be fairly small, on the order of maybe a kilometer in diameter to many hundreds of kilometers. These are often described as craters, but a crater is formed as a result of an impact event. And so really this is a type of sinkhole that's formed through subsidence and collapse, not something smashing into it. You often think of a crater as being at the top of a volcano, but it's really a caldera. And many volcanoes don't have these. It depends on the type of volcano. These types of caldera collapses are quite rare. Only 7 have occurred in the last 100 years or so. But they're quite spectacular when they do, as I said, because these things can be very large. And sometimes what happens is then, because the caldera is now often below sea level, it can be filled up and form a lake. So this is a volcanic lake when that happens. Now, another volcanic landform that is of quite interest are called columnar joinings. And this is a phenomenon whereby lava flows once they're crystallized, once they're solidified, form tall, thin, interconnected crystal structures, which are often hexagonal in shape. I'm not entirely sure why the hexagonal shape. I think it's just to do with the crystallization of the minerals, but I'm not 100% sure there. But these extend very far down from the surface through the solidified lava. And you can see these in certain locations when they become exposed. And they look like pipes, essentially, that have been cut like at different levels, except they're not cylindrical exactly. They're kind of hexagonal roughly in shape. And the reason these occur is because when the lava cools, it contracts, and thereby it forms cracks between the different segments. Again, I'm not exactly sure why they're so regular in width. If you see some photographs of these, they're quite regular in their sort of size. Not perfectly so, but to a high extent. And I think that this is because of if they cool at relatively the same time and relatively the same rate, then the size at which they crack is probably going to be similar. But again, I'm not 100% sure about that. But if you see these structures, then it's pretty much 100% that this rock was formed as a result of lava that cools and then contracts, forming these cracks surrounding it, it's pretty cool. And I'd recommend having a look at these on Google Images if you haven't seen them before, because they're quite beautiful. Now, the next type of volcanic feature that I'm going to talk about are volcanic plateaus. So plateau is just a big, wide surface, often high up, and these are formed by highly fluidic lava. So again, that's low silica content, kind of like forms your shield volcanoes. When these flow over a very wide region, they can form a plateau after they've crystallized and hardened. And typically this happens as a result of just extrusion of magma over a period of time without any very violent eruptions. Again, that occurs because of the low viscosity of the lava, so it doesn't have to build up pressure to a very high extent. Instead, it just extrudes over a period of time, an effusive eruption, remember, and then you get a big buildup of this magma, which forms a plateau. Now, that's a common way to form a volcanic plateau, but it isn't the only way. Another way that you can form a volcanic plateau is just if there's a mantle plume, like form the Hawaiian Islands, that builds up material in a magma chamber over time, pushing up the crust that sits above it, forming a plateau. So the plateau itself will not be made of volcanic material in that case. It's made of regular crust, which has been sort of pushed upwards. The final type of volcanic landform that I want to talk about here is a geyser, or geyser, depending on how you pronounce this thing. Now, a geyser is a spring. So it's basically a projection of hot water, and some steam, but hot water that comes out of the ground intermittently. So it's discharged, typically regular intervals, although some are more regular than others, when water is ejected violently and accompanied by ejection of steam. So geysers are fairly rare. They are formed at various places on Earth, but they're not very common because you have to have just the right combination of conditions for them to occur. So typically they're found near active volcano sites because the heat ultimately comes from contact of water with rocks that are very hot. So typically I don't think it's through direct contact between water and magma. That's more likely to lead to a volcanic eruption, as we talked about previously. That's one of the three mechanisms we talked about. However, if you have a magma chamber that's somewhere underground and there are rocks that are, surrounding that chamber, those rocks will be very hot. And if the water comes into contact with those hot rocks, then the water will warm up. So basically surface water moves down to a depth of usually around a few kilometers, so quite a ways down, where it comes into contact with these hot rocks and warms up. Now that in itself is not sufficient for a geyser. That can form a hot natural spring. But a geyser needs more than that because you need some mechanism to force this up to force the hot water up at regular intervals. So for geysers to form, first of all, you need rocks that surround the main sort of channel of the geyser to prevent the water from sort of spreading or percolating outwards too much, because then that's a way to relieve pressure. So you need the rocks to have the right composition to kind of keep the water in. Also, you need there to be quite a narrow neck or vent that connects the region where the water is making contact with the rocks and the surface. So this has to be quite a narrow tube. If it's too wide, again, it'll be too easy for the water to just then, the heated water to move back to the Earth's surface. And then again, you may get a hot spring, but you're not going to get a geyser. You need a very thin connection in order for there to be a very minimal ability for the water to then convect back up to the surface and cool down. So basically what happens is like a pressure cooker. The water percolates down and gets into the region where it comes to contact with the hot rocks, heats up, and normally it would let off some of that pressure by convecting up to the surface, but it can't do that, or only to a very limited extent, because of the restricted funnel, essentially, that allows it to get back to the surface. So the pressure builds up. Eventually, the pressure builds up to such an extent that some of the water sort of spontaneously boils, right? And then that comes up to the surface, breaks the surface, and then pushes some of the water up. Once the water's been pushed up, that slightly reduces the weight of the column of water that's sitting on top of it, and therefore releases the pressure. So it's basically like a positive feedback mechanism. You have just even a few little bubbles coming up of steam that releases the pressure, causing a feedback where a huge amount of the steam then spontaneously forms and rises up very quickly to the Earth's surface. So the water flashes into steam and violently boils up, resulting in an ejection of expanding steam and hot water, which then sprays out of the geyser. And that releases the pressure, and then after that's completed, I think eruptions usually take on the order of a few minutes. Once it's completed, then it settles down, and you'll have a gradual build-up of water again, which gradually heats up until the pressure sort of reaches a point where, again, you'll get spontaneous formation of bubbles, which then come up to the surface, and then the process repeats itself. So that's the reason why geysers can be quite regular. They're not always extremely regular, but some of them can be quite regular. It's basically because there's just a set amount of time it takes for the pressure to reach a critical level where you have the eruption. So that's a really cool phenomenon. And so we talked about calderas, we talked about columnar joining, volcanic plateaus, and geysers. All very interesting landform phenomena that result from volcanoes. Now, to conclude this episode, I want to talk a little bit about some of the interesting case studies of volcanoes. This is not a comprehensive list or anything. This is just sort of a selection that I've come across in my reading and that I think are interesting to talk about briefly. But before we get there, I want to briefly mention something called the Volcanic Explosivity Index, or VEI. And this is a metric that's used to measure the extent to which a volcanic eruption is explosive and how much, particularly what it measures is how much volcanic material is thrown out. And it's a logarithmic scale for most of the range. So that means if you increase the index by 1, for most of the range, it's 10 times more powerful, 10 times higher volume of material. So it ranges from 0 up to 8. And just like many of these scales, such as measuring hurricanes and tornadoes, and later we'll get to earthquakes, the more energetic it is, or in this case, the larger the volume of material that's extruded, the rarer they are. So for your low numbers, 0 to around 4, they're quite common. 1 and 0s happen basically all the time, especially in Hawaii, because these are low-level events that don't eject very much material, but happen pretty much constantly. So typically these are your effusive type eruptions, which are constantly releasing a small amount of material. Typically you have your low silica content. Typically that's going to be quite runny, often forming or adding to shield volcanoes, maybe some composite volcanoes as well. Levels 2, 3, and 4 are rarer. So by level 4, that happens maybe once every 18 months. And those are quite large eruptions, but still on the scale of things, not that large. So there you may be moving into your sort of intermediate magma with more silica content, but still not that much. So it builds up a little bit, the pressure builds up a little bit, but not too much before it's relieved. And so the amount of material ejected is still relatively small. A VEI of 5, which corresponds to an ejector volume of more than 1 cubic kilometer, is where it starts to get quite large. So Mount Vesuvius, which we've mentioned before, that's the one that in ancient Rome that covered all of those people, that had a VEI of 5, as did Mount St. Helens in 1980 in the United States, which is another quite well-known eruption. So these occur with a frequency of about every decade, so they're fairly rare, but not super rare, and tend to have plumes of extending up to about 10 kilometers, and it's at this point that you start to get significant injection of materials into the stratosphere. Now, if you recall from our episodes on the atmosphere, pretty much all volcanoes will eject at least some material into the atmosphere, into the troposphere, but that typically falls down fairly readily. It doesn't spread too far because the troposphere is where you have a lot of weather and wind and so forth, and that and rain and other things. That typically sort of causes the ejected material to rain out or fall out relatively rapidly. But when you get to the stage of VEI of 5, so your Mount St. Helens, your Vesuvius levels, Mount Fuji would be another one, at that point, you start to inject significant materials into the stratosphere, which is the level just above the troposphere. And the significance there is that there's not really much in the way of weather in the stratosphere. So once you're in the stratosphere, the material it stays there a lot longer. I mean, eventually it comes out, but it takes much longer, on the order of years, until it's removed from the stratosphere. Also, it will travel pretty much around the entire Earth once it reaches the stratosphere. So these level of volcanoes, 5 and above, are ones that are able to have a significant effect on the entire Earth, particularly the climate. Level 5, not so much. You will see some effects, but it's when we get to 6 and above that you start seeing really substantial effects on the Earth's climate. So as I said, Mount St. Helens, Mount Vesuvius, Mount Fuji, those are level 5. If we move up to the next level, which is 10 cubic kilometers of ejecta and above, that is the level of Krakatoa, which you may have heard of. That eruption occurred in 1883. That was an extremely large eruption, which occurred in an island in Indonesia. It destroyed most of the island that it was on and killed tens of thousands of people. So very severe eruption there, one of the most severe in recorded times. And it caused a volcanic winter across the entire planet, where average northern hemisphere temperatures fell in summer by about 0.5 degrees Celsius. That's at the level there, level 6, where we're talking about major global effects. So level 7, which corresponds to 100 cubic kilometers or more of ejected material, that is the next level up, and that is very substantial eruptions. Now, these only occur, level 6 occur at about once a century. These ones occur only about every millennia. So they are very rare. The last one of this magnitude was Mount Tambora, and that occurred in 1815. That eruption there, again, it was in Indonesia. That eruption had such a massive effect that it ejected so much material and ash up into the atmosphere, including particularly the stratosphere, as I said, it lasts longer up there, that it caused so much global warming that 1816 was called the year with no summer, particularly in Europe. Global temperatures, I think, went down, at least in parts of Europe, by about 3 degrees. Not everywhere, but in some parts of Europe. I think France was one of the worst affected, and it led to widespread famine in many regions of Europe. So that's the next level up again from the Krakatoa eruption. Another example of a level 6 eruption is Mount Pinatubo, and that was the second largest eruption on land in the 20th century. Not quite the same size as Mount Tambora, but about the same size as Krakatoa. And again, in this case, ash went up into the stratosphere, caused a 2-year reduction in global temperatures, and also had a significant effect on the ozone layer, which was a particularly big problem at that time. Interestingly, that volcano wasn't really known to be active at the time. I don't even know if it was known to be a volcano. The region was covered by so much vegetation that it kind of obscured the peak, and the native peoples who lived on the island were very heavily affected. I think they all had to be evacuated and only returned years later. So that's one of the more recent extremely devastating eruptions. Again, level 6, so same level as Krakatoa, Mount Pinatubo. That was in 1991 in the Philippines. Now, we already talked about Tambora. That is even higher, level 7, and that occurred about 200 years ago now. Now, the highest level, level 8, these are extremely rare, on the order of tens of thousands of years. One of the last of these to occur, I don't know if it was the last one, but it was one of the most recent ones of these to occur, and the largest explosive eruption on Earth in the last 25 million years occurred at Toba Lake, or Lake Toba in Indonesia. So this was level 8, which corresponds to more than 1,000 cubic kilometers of ejected material. It caused so much of a volcanic winter effect that it decreased worldwide temperatures between 3 to 5 degrees, and in higher latitudes up to 15 degrees. So remember I said that Tambora in 1815 reduced temperatures in parts of Europe by up to 3 degrees. Well, Toba Lake was up to 15 degrees, so you can see it's 5 times as significant in the higher latitudes as a result of all of that ejected material. And again, all of that's basically coming from the fact that there's so much dust up in the stratosphere that it's reflecting all of that light from the sun. It takes years for it to be removed. Now, there's a theory called Toba catastrophe theory, which says that this eruption, again, about 74,000 years ago, caused dramatic consequences for human population such that it killed almost all of the humans who were alive at the time. So this was before agriculture, but it was at a time when humans had spread over most of the planet. Not the New World, but most of the Old World, I think, had been populated by this time. But according to this theory, most of the humans who were living are killed, and it created a population bottleneck in East Africa and other regions. Now, it's not clear whether this is really correct. It's very hard to correlate the genetic evidence, which is, and I guess fossil evidence, but I think mostly the genetic evidence with the specific eruption. So it's not 100% whether this is actually what occurred, but nevertheless, this has been theorized and taken quite seriously. So it may be the case that humans almost went extinct because of this one volcanic eruption. And you have to wonder how many other species throughout history went extinct that could have been something impressive or significant, but just because of an ill-timed volcanic eruption or perhaps an asteroid strike. Anyway, Toba Lake, that is the single biggest volcanic eruption in the last 25 million years. And if that occurred today, it would be, it would solve global warming, at least in the short term, let me put it that way. But volcanic eruptions are very hard to predict. And as far as you know, any of these things could occur at any time. That being said, the probability is very low. As I said, one of these only occurs every 50,000 years or so. So it's not very likely. Now, there are a couple of other important eruptions that I wanted to mention. One of the Hawaiian Islands, I've kind of already talked about these. All of the Hawaiian Islands are basically just big volcanoes. Some of them are active and some not active. And as I said, they're formed as a result of these, thoughts have been formed as a result of these mantle plumes, these hotspots of activity with the mantle rising up and ultimately pushing up magma over the Earth's surface. And when this occurs in the oceans, leading to the formation of volcanic islands. And so you can go there today and see indeed some new islands that are forming or expanding as a result of this volcanic activity. These eruptions, however, are highly mafic or basaltic, similar term, and that means that they are effusive, so they don't build up a lot of energy. They happen regularly, but are fairly small in terms of intensity, and mostly it consists of lava that flows out and is fairly runny, and so it doesn't kill very many people. You can walk faster than the lava flows, but it does damage a lot of buildings and roads especially. So it does cause continued problems on that front. But as I said before, it's these unexpected, big explosive eruptions that, particularly with the hot and rapidly moving pyroclastic flows, that are the really dangerous ones. Now, there's one last eruption that I want to talk about. It's not even really an eruption, but it's closely related phenomenon called a limnic eruption, or a lake overturn, it's also called. Now, this is very rare. There's only a few of these have been documented to occur in any scale. I think this is the largest documented case. This occurs when dissolved carbon dioxide, which over time becomes saturated in a lake, suddenly erupts and is released from the lake, forming a gas cloud that spreads over a wide area and is capable of suffocating basically everyone, wildlife, livestock, humans, within that area. Now, one of these occurred at Lake Laos in Cameroon in 1986, when a large underwater landslide in the lake agitated or disrupted the carbon dioxide that was dissolved in the lake. That carbon dioxide having been formed as a result of gas ejection from volcanic sources. So basically, volcanoes, magma flows produce carbon dioxide, which then saturates the lake while that's dissolved in the water. I mean, it'll be kind of acidic, but other than that, it shouldn't be a problem. However, when there's a disruption that causes a large quantity of gas to be ejected out of solution, bubbles up out of the lake, then that produced a big cloud of this carbon dioxide, which spread across a wide area. I don't know exactly how wide an area, but like many kilometers surrounding the lake. And of course, carbon dioxide is invisible and odorless, so it's not really something you can notice or do anything about until everyone goes unconscious. And also because it's denser than oxygen or nitrogen, it moves along the side of the mountain near to the surface of the earth, and it killed over 1,000 people in a nearby town. From what I understand, the first people to arrive at the town, fairly isolated location, but whoever sort of initially went there just found everyone and everything dead, and no clear explanation as to what happened. Very creepy, if you sort of think about that. I don't know exactly how they determined that that's what happened, by the way, but to resolve this issue, a number of pumps have been installed in the lake, which help to pump the water out from the bottom of the lake and eject it into the air to help basically prevent a critical amount of carbon dioxide being dissolved. This phenomenon has occurred in a few other lakes, I think all in Africa as well, but I think this is the case that killed the largest number of people. So very scary phenomenon, but it's not something that you should worry about because it's highly unlikely that anything like this is located near you. But it's very interesting, so I thought I would mention it. That's called a limnic eruption if you're interested in looking it up further. So before we finish out this episode, let's just summarize some of what we talked about. The main thrust of this episode has been talking about the different types of volcanoes and types of eruptions, as well as some of the landforms that are formed as a result of volcanic activity. And in particular, we focused on the composition of the magma as a unifying factor that determines both the type of eruption and the causes of the eruption, where the eruptions typically occur, as well as the types of volcanoes that they give rise to. In particular, we talked about how the silica content is critical. The higher the silica content, the more viscous the lava is, the thicker it is, and the more resistant to flowing it is. And therefore, the more it tends to build up and reach a sort of critical pressure in the magma chamber or in the sort of vent above it, causing, when it finally does release that pressure, very violent eruptions which eject a huge quantity of material and rock and magma over a wide area. Conversely, the lower silica or basaltic magma, which is runnier and thinner, doesn't build up very much and is more released in smaller amounts in what are called effusive eruptions, which tend to form these big, wide shield volcanoes instead of the lava domes, which have kind of the big crater in the middle formed by the viscous lava. And then you've got the composite volcanoes, which are kind of in the middle, which have a combination of tephra as well as lava flows that sort of build up on top of each other. We also talked about pyroclastic flows and their dangers. We talked about different types of lava. We talked about the different causes of eruptions, particularly how they can form as a result of decompression of gas or interaction of water with the magma, or superheating of steam, which then explodes and releases pre-existing rock without releasing new magma per se. We also talked about some of the different volcanic landforms, including calderas, columnar joins, volcanic plateaus, and geysers. And finally, we talked a bit about the volcanic explosivity index and had a bit of a tour through some of the different levels of explosivity and reaction there, and talked about some of the particularly prominent eruptions that have occurred recently, including Mount Pinatubo, Tambora, the Hawaiian Islands, and Toba Lake and Krakatoa. So hopefully you found this episode of interest. If so, feel free to leave a positive review on iTunes or Spotify or whatever aggregator that you prefer to use. You can also send me an email. My email address is fods12@gmail.com. That's fods12@gmail.com. I'm happy to hear any questions or suggestions, feedback, or anything else you'd like to say. Finally, if you'd like to support the show financially, consider becoming a Patreon supporter. You can see a link in the show notes to my Patreon, or just Google Patreon, the Science of Everything podcast, and you should be able to find that. Or you can make a one-off donation via PayPal if that's what you prefer. I greatly appreciate all of the generous listeners who make a donation to help to keep the show going and to help me to devote a bit more time to it. So once again, thanks very much for listening, everyone. The next episode coming up hopefully pretty soon will be on earthquakes, as I promised, so look forward to that one. Take care, and I'll talk to you next time.